Hello, everyone. Good morning, good afternoon, wherever you are. Um, this is the MagnaFlux webinar for 10 misunderstandings about magnetic particle testing. My name is Wyatt Burns. I am the Equipment Product Manager at MagnaFlux. I work out of Glenview, Illinois, and I've been working for MagnaFlux for over 3 years now, specifying in the equipment, so magnetic particle inspection, liquid penetrant inspection, and I'll let my colleague introduce himself.
Yes, my name is Richard Reidenauer. I'm working out of California for MagnaFlux. So um, got I'm a former level 3 in the organization, or not in with MagnaFlux, but in my prior lifetime, but working with MagnaFlux directly for about 10 years now. And I'm overall sales manager for the Western region of the US.
So, as part of this, we thought it would be fun for everyone on the call to type in where they're from on the broadcast, so we can kind of get a feel for, where our attendees are at, because this is a global webinar and we want to reach out as far as we can. So, if you get a chance, go ahead and type in where you're from on that Q&A panel. And just a side note, Richard and I are going to go through these 10 misunderstandings, and then at the end, we will be answering questions. So if something comes up, pops in your head, go ahead and type it into the Q&A section. And with that, we'll get started with the 10 misunderstandings. The first misunderstanding is that all metals can be used in magnetic particle testing. So the real first question to ask when you're looking at magnetic particle inspection is, can it be magnetized? The thinking that all metals can be magnetized is a big misconception, likely stemming from the fact that most, if not all, metals conduct electricity. The fact that metals have an ability to retain magnetization also grants it the ability to produce a magnetic field. This invisible magnetic field is what MagnaFlux uses to guide our magnetic particles to indications on the part. Without that field, magnetic particle inspection will not work. The most common metals that can be magnetized are iron, nickel, cobalt, along with most of their alloys and some forms of steel. Aluminum is non-magnetic. You're going to have to use liquid penetrant or another method to test those parts. If you want to check your material, the easiest way is to grab a small household magnet and try sticking it to the part. We have this chart here for reference, just in case you have a question. There's a lot of metals out there. Again, not all of them are able to be used with magnetic particle inspection.
So the next slide we have here is your bath doesn't need to be changed. Contamination is in every environment, and no matter how clean your space or parts are, oils, grease, sands, dirts, and other solids will be introduced to your bath by inspected components. So oil in a water bath and vice versa is a primary concern as well. These unwanted contaminants can hinder testing performance and disguise indications. Examining the carrier and bath during daily bath concentration checks by looking for differences in color, layering, or banding in either the carrier or the particles, you can spot contamination. If there's a band that fluoresces brighter than the bulk of the material, then there's an excessive unattached fluorescent pigment and the bath should be changed. So one of the ways that you can do this is to strictly take your centrifuge tube in the stand. You have your graticles that are normally in the front side so you can read your particle concentration, and simply just turn the centrifuge tube to where the graticles on the back. You should still be able to read the graticles. If you can't, you definitely need to be changing your bath. You get I have in the past, I've actually ran my bath for close to a year with very clean parts going in and try to keep all contaminants out. But after a year, what happens is the epoxy layer on the particles actually separates so much it starts getting onto the parts. You start getting background fluorescence, and you definitely have to change everything out. So.
All right. The third misunderstanding we have is that more current is always better. And when we say current, we're talking about the amperage sent through the part. So, it's a misconception that sending more current through the part is always better, but it's not. There's definitely a sweet spot, and it takes some time and practice to get just right. The fluorescent particles in our MPI baths are mostly attracted to the magnetic field flux leakage caused by the discontinuities in the material grain structure, aka an indication. However, the rest of the magnetic field will also attract particles to the surface of the part. So just because you have a little bit of flux leakage due to that indication doesn't mean that's the only area where iron particles will be attracted to the surface. So it has the potential to create a bright background if you use too much current, and it makes it difficult for the operator to find indications they're looking for. So we have in this picture kind of a good comparison of what a part with kind of the ideal amperage versus a part with just maximum amperage. So on the left here, this is a part that was inspected with a lot more amperage than needed. And you can see that the indication, there's two indications here, but both of them are a little bit more difficult to see than the ones on the right. So the one on the right, you got right to that sweet spot of the amperage you needed to hit that 30 to 60 Gauss magnetic field reading. So really just the misconception is that you always want a magnet with more amps, but the truth is you really just want to try and get to the amperage level that creates a 30 to 60 Gauss reading on your part.
Okay, so all materials magnetize the same way. This is not true. I've actually seen what's really funny, parts that have come in a lot, and by lot I'm talking about as one part number coming through, and the heat treat made a difference, where you find some parts that are actually heat treated and some are not. It'll actually change the way that you view the material itself. So you can have parts that are the same way, are in the same shape and form, but they could be made of a different material even, and they're not going to have the same test method. So this is because varied materials have different permeability and retentivity. So permeability actually affects how easily the magnetic current travels through the part and gets attracted to the small flux leakages because of flaws. And then your retentivity of a material is how well it's hanging on to that magnetic field. So to ensure the parts are properly tested, double check the material. Do not assume that the same technique can be used on similar looking parts. For instance, in the fastener industry, you have many different fasteners that can look all the same, and they have many different materials. So you have to be careful of that. Tools to identify that: QQIs, flux indicators, Hall effect meters, etc. And also watch for your patterns on the part, which kind of ties into Wyatt's last slide that he showed. Wyatt?
Okay. So the fifth misunderstanding is that part cleaning is not necessary. So technically, it's not necessary, but it's extremely recommended. Pre-testing part cleaning is a key part of the process to ensure the highest probability of detection. When you have oil, metal shavings, or other contaminants that can find their way seeping into the smallest indications before testing, it makes it really hard, if not impossible, to identify them. Additionally, cleaning parts beforehand will decrease contamination in your bath. This this reduces the changeover and maintenance time to keep it at appropriate contamination levels. This is similar to what Richard was discussing earlier with the centrifuge tube. Ultimately, ensuring you have a clean part before testing will reduce your percentage of missed indications and the amount of bath changeovers required due to contamination. So at the end of the day, some people look at cleaning their parts before testing as an added cost, an added, time, and another step in the process. But really, it's a huge improvement. It increases your chances of catching any indications, and it really has the potential to decrease your costs by not letting any parts slip out the door. So, we really recommend part cleaning, and there are plenty of methods to do that. So we can get into it later if anyone has any questions.
So slide 6, you can mag through coatings. According to ASTM E709-15, thin non-conductive coatings such as paint in the order of 1 to 2 mils will not normally interfere with the formation of indications, but they must be removed at all points where electrical contact is made for direct magnetization. It must be demonstrated that unacceptable discontinuities can be detected through the maximum thickness applied. So just an add-on to that, you can definitely, you're more susceptible to see indications using like a yoke without taking your coatings off. But I did an extensive study on a part that had failed in the past, and we were doing, the mag was actually being performed with a prod inspection through mill scale, and we were not seeing any defects. They took the mill scale off, and which was approximately, I believe it was in the neighborhood of 7 mil. And when they took the mill scale off, there's actually a formation, a 7-foot long crack actually formed with the fluorescent particles, but yet with the mill scale on there, we couldn't see anything. We determined through that study that it was about 5 mil of thickness, that you could actually still see parts going through a coating. But again, when you are dealing with mag particle and you're dealing with a coated surface, if something is seen, it should always be cleaned and verified. I would never feel comfortable certifying a part if it did have a coating and I saw something. I would want to make sure that that coating is taken off the surface and re-inspected and verified for the indication. Wyatt?
Awesome, thanks, Richard. So the 7th misunderstanding is that you must always do 2 shots. And when we say shots, we mean magnetic shots. So firing some amperage through the part. So depending on your part and the application, this might be true. You might need to do 2 shots. Very large parts requiring 3-phase full wave DC at high amperages will likely need to be magnetized twice in order to inspect in either direction. However, with the advent of multi-directional or MD units decades ago, the inspection time of many smaller parts was dramatically reduced. So without multi-directional capabilities, the longitudinal and circular magnetic fields created by a mag shot would cancel each other out. This in turn also eliminated any residual magnetization holding particles around indications. Therefore, an inspector would need to mag, inspect, then mag and inspect for cracks in the other direction. So the picture we have here is of QQIs on the same part, and as you can see, the indications visible are in opposite directions. So this would show an example of when you mag it with a headshot and then you inspect and then you pull in your auxiliary coil and mag it again. So multi-directional technology allows you to fire multiple mag shots that do not interfere with each other because they're out of phase. So you press the button once and it fires the mag shot in both directions, and they're out of phase with each other, so it does not cancel the other magnetic field out. It takes some balancing of the magnetic field strength due to the part geometry, but ultimately leads to inspection in about half the time. So there definitely is a fine line between whether or not you want to use multi-directional units. It typically depends on your part geometry and the volume of testing you're doing, because setting up one of these tests does take a little bit longer, because you have to sit there and balance the field with the QQI and make sure that you're going to see the both directions on the QQI. So if your volumes don't dictate it and your part geometry is too complex, you don't want to do two shots, but or you do want to do two shots. But if you can get away with it, multi-directional allows you to do one shot and save a ton of time, because you're going to be able to see the full cross or the concentric circles on the QQI here in one shot.
I apologize. I'll be right with you. I've lost my video, so it's coming up now.
No problem.
Okay. So daily system performance checks are not crucial. This is, I hope everybody understands how crucial they are. You know, it doesn't take much to have a machine fail on the electronics underneath. And you don't know that unless you perform these daily checks. If you're running a Ketos ring for your daily check or whatever it may be, or even your black light intensity, this is a very, very critical step before you even start doing any type of inspection. So, and that's the reason why ASTM and NEDCAP require your quality checks to be not only performed, but also recorded. You want to check your daily checks are also to ensure your bath and machines are in proper working condition. You want to verify your bath concentration, your lamp intensity daily on every shift. You know, a lot of that, when you had your mercury vapor bulbs, that was even more critical. Your LED lights are more stable. They don't drop in intensity like your mercury vapors do. But even still, you still have to, it is written in your specs that you still have to perform that check. You know, you don't know if you're running two shifts and your night shift happens to drop the light and knocks an LED diode out, it could affect your overall intensity. So just be careful of your daily checks. Also, you also have white light, and you know, if you got too much extraneous white light, that can affect the ability to see indications. So basically, your daily checks can save time and money in the long run. I've actually experienced it where an entire shift of work was because somebody didn't perform a daily check. The amp meter was reading 1, but the machine was not really putting out, and all those parts basically had to be re-inspected because we had an inspector that wasn't doing his job. So very, very critical operation, very simple operation to do, and keep your quality in check when you're doing mag particle. Wyatt?
Awesome. So yeah, we do have some pictures here. We got light meters, and we got the centrifuge tube that Richard touched on earlier. Then we got this the shunt meter. So this is a 6-month calibration that still needs to be done. It's not daily, but it definitely ensures that your ammeter is measuring correctly. So just some examples of different calibration tests. All right, number 9, the 9th misunderstanding. Adding particles makes it easier to detect indications. So more particles are not always better, similar to the amperage discussion we had earlier in the slides. Adding too many particles to the bath will add too much concentration, and you'll lose the ability to see small defects because of the excess background. So similar to having too much amperage, having too many particles will also increase the amount of background on the part, making the contrast between any indications a lot less significant. So it is better to replace the entire bath and slowly add more particles until the correct concentration is met. This does take a little bit of time, but it saves so much more time in the long run and makes it so much easier on your operators to find any indications that there might be. So it is very crucial to get within the range of your concentration. So there are different ranges out there, but you want to stick within whatever your specification is.
Okay, our 10th slide here, multi-directional units are always better. As a salesperson, I can verify how many people have this misconception that, hey, this is great. I can do 2 shots at one time. I can save all this time. And if you're doing a tremendous amount of parts, that is absolutely true. If you're doing a few parts, not large lots of parts, that is completely false because of the setup time that it takes for you to calibrate your multi-directional machine. So where I'm going with this, you have to have what is called a balance field with multi-directional. Balance field is very critical for the success, because what happens in multi-directional setup is if you have one field, you have longitudinal, you have circumferential fields, the flux flows will actually hit those simultaneously, bam, bam, one right after the other. But if you have them where they're out of balance, what happens is that last shot, whichever shot it may be, will actually take away what the first shot did if they're not completely balanced. So you don't have one overpowering the other field. So to do that, it takes a long time doing repeated shots, looking at your QQIs and making sure you have a good crosshair or a circular pattern on your QQI. Once you have that, then you can start your inspection. But here again, if you're doing parts on a continual basis, and you're thinking that you want to always start your inspection with a QQI test, even though you've done those parts, the same parts you did yesterday, you still want to start your test with a QQI check or a balancing of the field. For complex part designs and smaller volumes, it's absolutely more time savings by doing conventional mag particle inspection using a head shot and a coil shot. You can actually save time instead of trying to balance a field. A lot of times you're looking at a minimum of a half hour to set your multi-directional units up. So this is it's a very, a lot of people that are asking for multi-directional don't understand this process. So we just wanted to make sure that people did understand that. Be careful when you're asking for multi-directional units, so they don't work for everything.
Right. Just to tag on there, it ultimately is up to the responsible level 3 to write the technique for inspection, but Magnaflux is willing to, openly discuss applications and give some feedback and potentially even help with testing if you are considering multi-directional versus the standard unidirectional units. So just reach out if you have any questions on this. Again, we won't write the technique for you, but we can offer some input on what considerations to have. So, all right. So that kind of concludes the 10 misunderstandings of magnetic particle inspection. And now Richard and I are going to move into answering some questions. So as more questions pop into your head, feel free to submit them to the Q&A. And if we don't get to them, we are more than happy to answer them individually. We have our customer service contact information here. They're very responsive, very helpful, great people. So if we don't get to your question now, we're more than happy to answer it one-on-one. So looks like the first question is, if water is the carrier, does pH or hard water affect the solution? So Richard, do you want to answer this one?
Yes, absolutely it will. Um, it you want to try to keep, well, first of all, hard water. I'm not a proponent of the water carrier because it takes so much maintenance to keep that in a mag machine. And, you know, when you add water, you add an electrical current, you add iron particles, excuse me, that is you've got a lot of components that will lead to corrosive nature in your machine. But your hard water, not only will it, we actually have water softeners that we like to, or water conditioners that we add into your water bath to help that out. So yes, hard water will definitely make a difference.
Right. Just to add on Richard's point about not recommending water carriers, from an equipment standpoint, it will also degrade your equipment much faster. Not only does the carrier act as a better medium for the magnetic particles with better wettability and maintaining the part health, but it will maintain your bath health and reduce the corrosion and increase the life by, who knows, some of our equipment lasts 50 years so and more. So carrier is definitely a better option. But yeah, so let's move on. The second question, what is an example performing MPI on aluminum? Industry, type of part. So again, aluminum is non-magnetic. You can't use MPI on aluminum. If you do need to test aluminum, we recommend liquid penetrant inspection. There are a ton of examples in the automotive industry of high volume liquid penetrant inspection with aluminum parts. They're, easy to make, lightweight, really strong, but they're not magnetic, so you can't use magnetic particle inspection on them. So the third question, if I am trying to magnetically test a galvanized part, is the galvanized reducing my ability to find indications? If so, how can I maximize my ability to see indications since I cannot remove the galvanized coating?
So I'll take that one there. It is, once again, the one component that's not listed here is how thick is the galvanized. I have performed mag particle on galvanized parts, but I've also seen where the parts were so galvanized and a very thick coating that it did affect it. It is recommended not to do mag inspection on a galvanized part. So I see that the question actually says I cannot remove the galvanized coating. So my only suggestion there is you can still perform it. You would have to list it. If you're certifying these parts, you would have to list the conditions on your certification. And hopefully that if you had basically parts that had a defect from day one, you're probably not going to see that because the galvanized coating will cover that up. But if you do have a crack in the part or a fatigue, some sort of a fatigue defect, chances are it's going to actually crack the galvanizing also, and you will still see the indication. But here again, on the certification, never would I actually certify and not make a note that the parts were galvanized.
So any sensitivity difference between oil and water-based carriers? Richard, you want to take that one?
The difference between oil and water-based carriers, yes, there is a big difference of how the particles suspend on the parts themselves. So with oil, you have a much better particle mobility than you will have with water. So here again, that's another check mark against why I don't really care for the water-based carriers, but I also understand that there's times from an environmental standpoint that some businesses just will not use the oil in their business and they must use the water, and it's better than nothing at all is the way I look at it. So
Right. Okay, cool. So the next question we have here is some machines are designed using peak current waveform, others RMS, root mean square. Does 1000 amps RMS result in the same or different magnetic field than 1000 amps peak waveform? So to answer your question, really what matters is the amperage that is read through the part. So your shunt is going to read the amperage and display it on your ammeter, and that's really all that matters. So the RMS versus peak amps is really just a specification. So we can put both on our product data sheets. What really matters is the reading on your ammeter. So if you see 1000 on the ammeter, it's going to produce, and it's the same part, considering there's different parts that will react differently to the same amperage. If you have the same part and the machine reads 1000 amps, it will produce the same magnetic field. The RMS versus peak amps is really just a data point, right? So typically we do RMS rather than peak amps on North American equipment. Let me see.
So I'm going to take this one here, Wyatt, that's got multiple questions.
Okay.
We have somebody who's mentioning the fact that he had a customer from Korea that insisted that he did mag particle on their aluminum parts, which they had been doing mag particle for years. And that's actually that's happened to me in the past, where you get parts that come in and people say, well, I've done this for years. Well, you're the person inspecting and certifying those parts. So just be wary. Not everything that you see might be the correct way to do things. We find that a lot in some of our different markets, where you get people that, well, 20 years ago, I was taught by this guy, this is how to do it. Well, 20 years ago, that doesn't mean it was correct. So be careful of that. His second question, do sandblasted parts need to be cleaned, or does the sandblasting render the surface acceptable? That's a yes and no. Some of your, if you look at some of your parts, if you have a coated surface and you sandblast it, absolutely you're going to get a better mag particle. But if you're looking for very fine, tight defects, there is a possibility that sandblasted parts will actually, you can take and deform the metal and close an indication up. So something you have to be careful of. What you would normally want to do is take a part, put known defects in, sandblast it, and make sure that you're getting what you call a known defect standard, and verify your technique that way. Does shelf life retentivity affect thinner sections differently than thicker on the same parts? I think what you're saying is if you have different thicknesses, is your retentivity, which is the holding of the mag, is that going to affect, is it going to be different from a thin section to a thicker section? It's basically the material itself is holding on to the magnetism. It's not the difference in thickness. So the one thing that I would have to say there, however, is your thinner materials are going to receive more magnetism than your thicker materials, unless you're doing separate shots. So does QQIs work with alternating current inspection? Yes, QQIs will work. They actually work very well, because AC is a surface field. So, and the QQI is on the surface, so it'll work very well.
Quick question here. When you install a new MPI unit, which direction should it be installed? The direction of east or south or north makes any earth field issues. The magnetic field of the earth does not really affect this, so just install it whichever way is ideal for you. Okay, what about subsurface indications? How deep can MT see flaws below the surface?
Many different answers to that, depending on your permeability in your material. How well does that material take the magnetic field will determine how deep you can go. I have actually experienced using prod inspection a lack of penetration line that was almost 3/8 of an inch deep. So it can definitely see subsurface. You have to be experienced when you're looking at that because it does not look like a nice fine sharp line. It's a very broad and fuzzy line. You just know something's there. Lack of fusion you can see along the sidewalls of welds, that sort of stuff. So but I wouldn't say that every part you're going to see 3/8 of an inch deep. That just happened to be a circumstance that was just the penetration was it was very, very pronounced, and the broad fuzzy line was very pronounced. So we were able to find it, but chances of going, I would realistically say on like your foreign parts, castings, forgings, stuff like that, you're probably in the neighborhood of about 1/8 of an inch that you can see relatively easy. 1/4 of an inch, if you look at your Ketos ring, you've got some indications that actually go down to 3/8 of an inch. 1/4 of an inch can be seen as long as you're doing the proper technique. So if you don't have enough amperage, you're not going to see anything under the surface. So a lot of factors there on seeing subsurface indications. Using an AC field compared to a DC field, so that's another factor. So
awesome. Okay, so it's 9:45. With that last question, we're going to conclude and wrap up this session. We thank you all for attending. We really appreciate everyone asking questions and really supporting what we're trying to do here. If we did not get to your question, please leave your email with your question. You can just go into the Q&A section and reply to your own, and then that will give us a way to contact you with the answer. And just watch out for future events by subscribing to our blog and following us on social media sites. We're on Facebook, Instagram, Twitter, LinkedIn. So, we're here. We want to talk to you. Always use this support@magnaflux.com email with questions or call. With these times, we want to keep talking to you and be the best help we can. So thank you all. And with that, take care.
thank you.